Welcome to all of you. Now we discuss about 2021 paper CC-9 Group B partial differential equation semester 4 mathematics honors. Question paper 2021 paper CC-9 Group B. Question 2a. Form the partial differential equation by eliminating the arbitrary function f from the equation z equal to x f of y by x. Z equal to x f of y by x, differentiating 1 partially with respect to x and y respectively, we get del x z equal to x f dash y by x into minus y by x square plus f y by x, and del y z equal to x f dash y by x into with respect to y, so this is equal to into 1 by x. Equation 3. From 3 we get f dash y by x equal to del y z. X and 1 by x cancel each other, and from 1 we get f y by x equal to z by x. Using this, from 2 del x z x into f dash y by x, so value of f dash y by x equal to del y z put here, and this minus y by x square, this x and this x square cancel each other, and value of f of y by x equal to z by x, and put all of these values, and the simplification we get x del x z plus y del y z equal to z. This is the required partial differential equation. Next question 2b. Find the solution of the equation bracket y minus u into ux plus bracket u minus x into uy equal to x minus y with the Cauchy data u equal to 0 on x into y equal to 1. The system of characteristic ordinary differential equation Chaput-Lagrange method is dx by y minus u equal to dy by u minus x equal to du by x minus y. This is the corresponding system of characteristic differential equation. From this, to find the first characteristic equation, we write dx by y minus u equal to dy by u minus x equal to du by x minus y. This equal to dx plus dy plus du whole divided by y minus u plus u minus x plus x minus y, so this equal to 0. Hence dx plus dy plus du equal to 0. This implies x plus y plus u equal to c1, where c1 is an arbitrary constant. To find second characteristic equation, dx y minus u equal to dy u minus x equal to du x minus y equal to x dx plus y dy plus u du divided by x into y minus u plus y into u minus x plus u into x minus y. After simplification, this is equal to 0, denominator equal to 0, hence x dx plus y dy plus u du equal to 0, and we can write this half into d, x square plus y square plus u square equal to 0, hence x square plus y square plus u square equal to C2, where C2 is an arbitrary constant. Equation 2 and equation 3 give two characteristic equations of the given partial differential equation. To find the general solution of the partial differential equation, the general solution of the given equation 1 as given by phi of C1 and C2 equal to 0 in implicit form, or equivalently we can write C2 equal to some function f, capital F of C1, where phi and f are arbitrary functions. Therefore, this C2 is equal to x square plus y square u square equal to capital F of C1, C1 equal to x plus y plus u. So we can write this equation 4. Now, with the condition this u equal to 0 when x, y equal to 1. The given condition is this. So from this we can write u equal to 0, put u equal to 0 when x into y equal to 1. So this x square plus y square equal to f of x plus y, because u equal to 0. And put y equal to 1 by x, because x into y equal to 1. So x square plus 1 by x square equal to f of x plus 1 by x, equation 5. Set capital X equal to x plus 1 by x. Then capital X square equal to x plus 1 by x whole square is equal to x square plus 1 by x square plus 2. So x square plus 1 by x square equal to capital X square minus 2. And we get capital X square minus 2 equal to capital F of x, because this capital F of x plus 1 by x equal to x square plus 1 by x square. So we can write this x plus 1 by x equal to capital X. So put here capital X square minus 2 equal to f of capital X, equation 5. So capital Fx is determined, because capital Fx is of the form x square capital X square minus 2. So this x, so here is x. So here is argument of f, capital F is x plus y plus u. Then in place of capital X we can write x plus y plus u whole square minus 2. From 4 and 6, this is the 4, equation 4, and this is the 6. We can write this x square plus y square plus u square equal to x square plus y square plus u whole square minus 2. So cancel each other. This expanding this x square plus y square plus u square twice xy plus twice xu plus twice yu minus 2. Cancel each other term this. So we get 2 into u bracket x plus y equal to 2 into bracket 1 minus x into y. So u equal to 1 minus xy by x plus y. Hence the required solution is u x y equal to 1 minus xy whole divided by x plus y. Next question 3a. Apply Char-Pitts method to find the complete integral of the partial differential equation px plus qy equal to pq. Let f x y z p q this equal to pq minus px minus qy equal to 0, equation 1. Now Char-Pitts auxiliary equations are dp by fx means del f del x, plus p fz equal to dq by fy plus qfz equal to dz by minus pfy minus qfq equal to dx by minus fp equal to dy by minus fq. Hence this dp by minus p, by simplification this, because fx means the partial difference reading with respect to x, so fx equals to, we get minus p only, and fz equal to 0 because there is no z here, so only minus p, and fy equal to minus q, so this fz equal to 0, and similarly other terms. So this p into minus p into q minus x, fp, q minus q into fq, p minus y, and this minus bracket q minus x minus bracket p minus y by equation 1. Taking first two ratios, this and this, so we get dp by p equal to dq by q. Integrating, we get log p to the base e equal to log q plus log c. Here logarithm to the base e, natural logarithm. This equal to, this implies p equal to c1 q, where c1 is an arbitrary constant. From 1, given equation from 1, we can write this using 3, is c1 q square equal to q into bracket c1 x plus y. Put here p equal to c1 q, p equal to c1 q. So we can write this c into q square equal to this. So q equal to c1 x plus y by c1. Therefore dz equal to del z del L x z dx, p means del L x z dx plus del L y z dy. So value of p is this, this value of p is c1 into dx by 3 and 4, this p into dx, p is equal to c1 into q, and this q equal to c1 x plus y whole divided by c1, so c1 cancel, so we get c1 x plus y dx plus q into dy, q is this, into dy. So we get c1 x plus y divided by c1 into bracket c1 dx plus dy. Now putting t equal to c1 x plus y, so dt equal to c1 dx plus dy. Hence dz equal to 1 by, dz equal to this, so dz equal to 1 by c1 x equal to y plus y equal to t, and this equal to dt. And integrating this, we get z equal to t square by twice c1 plus c2. c2 is an arbitrary constant. So z equal to 1 by twice c1, value of t is this c1 x plus y, so c1 x plus y whole square plus c2. This is the required complete integral. Extra, you can second complete integral in this way, but it is the extra, this taking second and fourth ratio into, we get dq by q equal to dx by q minus x, implies q into dq minus x dq equal to q dx. So q dq equal to d of x into q. Integrating, we get q square by 2 plus c3 by 2. C3 is an arbitrary constant, and this x into q. So we get q square minus twice q x plus c3 equal to 0. So this is the quadratic in q, solving by Sturgeon formula. So q equal to ax plus minus whole root over x square minus c3. Taking the positive value, so we get q equal to x plus root over of x square minus c3, equation 6. From 1 using 6, from the given equation 1 using 6, we get p into value of q is this, put here, minus p x minus y into value of q. So after simplification, p equal to this, equation 7. Now dz equal to p dx plus q dy, so value of p equal to this, and value of q equal to 6, from 6 this, and put all these values here, and after simplification you get dz equal to d of xy plus d of y root over x square minus c3. integrating we get z equal to xy plus y into root over x square minus c3 plus c4. C4 is an arbitrary constant. Next question, question 3b. Solve the partial differential equation ux square plus uy square equal to u using uxy equal to fx plus gy. Let uxy equal to fx plus gy. So now ux means ddx f and uy equal to ddy g. This is the total differential ddx because this a is a single variable of x, so not del x. This is the ddx, and this plus gy a single variable of y, so uy equal to ddy g. Now ux square plus uy square equal to u. So from 2 we get, using from 3 we get ddx f whole square plus ddy g whole square equal to fx plus gy. So ddx f whole square equal to fx and ddy g whole square equal to gy, comparing both sides. So ddx f equal to root over of fx, this implies df by root f equal to dx. Integrating we get 2 into root f equal to x plus c is an arbitrary constant, so f equal to x plus c whole divided by 2 whole square. Similarly we can get g equal to y plus d by whole divided by 2 whole square, d is an arbitrary constant. Hence u equal to f plus g, so f equal to this and g equal to this, so u equal to this. This is the required solution. Check. From 6 we get ux. From ux we can write 2 into x plus c by 2 into 1 by 2. This is equal to x plus c by 2, and uy equal to this 2 into y plus d by 2 into 1 by 2. So ux square plus uy square equal to this square plus this square, so this is equal to u, hence verified. Alternative method. Now it is the extra part. Ux square plus uy square equal to u. Let u equal to f of x plus ay. This is equal to f b, say, where b equal to x plus ay. Now ux equals to ddvf into ddxv, so ddvf, because ddx of v equal to 1, v is this, so ddx of v equal to 1, and uy equal to ddvf into ddyv. This is equal to a into ddvf because ddyv equal to a. From this, using this, from 1 we get ux square plus uy square equal to ddvf whole square plus a square ddvf whole square equal to f. This is equal to f, so because f equal to u, so ux square plus uy square equal to u, so u equal to f, so we can write this ux square plus uy square equal to u, that is equal to f. So ddvf whole square into bracket 1 minus a square equal to f. So ddvf equal to root over square root f by 1 plus a square, taking positive value. So square root 1 plus a square equal to df by root over of f equal to dv. Integrating we get root over of 1 plus a square into 2 into root over of f equal to v plus b. B is an arbitrary constant. Squaring we get 4 bracket 1 plus a square into f equal to v plus b whole square. So after simplification we get u equal to bracket x plus ay plus b whole square whole divided by 4 into bracket 1 plus a square. A and b are arbitrary constant. So from this we get a equal to this, and from this u equal to x plus c by 2 plus y plus d by 2 whole square. And from this way we get this result u equal to this. Next question. Question 4. Reduce the second order partial differential equation y u x x plus bracket x plus y bracket close u x y plus x u y y equal to 0 to a canonical form and hence solve it. Comparing the given equation with a u x x plus b u x y plus c u y y plus f of x y u u x u y equal to 0, we get, so a capital A equal to y, capital B equal to x plus y, capital C equal to x. And then discriminant b square minus 4ac equal to x plus y whole square minus 4xy equal to x minus y whole square. This obviously greater than 0 because x not equal to y. We assume here x not equal to y. Hence the given partial differential equation is hyperbolic everywhere except along the line y equal to x. Because this discriminant is positive, so this is hyperbolic. And it is parabolic when x equal to y, that is on the line y equal to x, as b square minus 4 is equal to 0. Now the alpha quadratic equation a lambda square plus b lambda plus c equal to 0, this is equal to y lambda square plus bracket x plus y lambda plus x equal to 0. So lambda equal to, by Siddharth formula we get this equal to minus bracket x plus y plus minus bracket x minus y whole divided by 2y, this equal to minus 1 and minus x by y. This is minus 1 say lambda 1 minus x by y equal say lambda 2. Two roots of this lambda quadratic equation. And corresponding characteristic equations are respectively ddxy plus lambda 1 equal to 0, ddxy plus lambda 2 equal to 0. Now lambda 1 equal to minus 1 and lambda 2 equal to minus x by y. So ddxy equal to 1 and ddxy equal to x by y. So dy equal to dx, and from this y dy equal to x dx. Integrating respectively we get, from this we get y equal to x plus c1, and from this y square equal to x square plus c2, where c1 and c2 are arbitrary constants. So c1 equal to y minus x, and from this c2 equal to y square minus x square. Choose xi equal to y minus x and eta equal to y square minus x square. Hence xi x, that is means del x xi equal to minus 1, xi y equal to 1, eta x equal to minus 2x, eta y equal to 2y, equation 2. Now del x u equal to del xi u into del x xi plus del eta u into del x eta equal to minus del xi u minus twice x del eta u by 2, and put these values of this xi x, that is xi x means del x xi equal to minus 1, and this eta x means minus 2x, and put all these values here. So after simplification we get, and del y u equal to del xi u into del y xi plus del eta u into del y eta. So xi y and eta y, xi y equal to 1 and eta y equal to 2y. So from this we get del y u equal to del xi u plus 2y del eta u. Now del 2 del x square u equal to del x into del x u equal to del x. This del x u equal to from 3 minus del xi u minus 2x del eta u, put here, and this simplification minus del x del xi u minus 2 into x with respect to x, derivative partial to 1, so del eta u minus 2x into del L x of this. So minus del L xi into del L xi u into del xi del x minus del L eta into del L eta of del L xi u into del L eta del x. So from this term we get this term, this del L x, we can break up this del L xi into del xi del x minus this del L eta into del eta del x, and from this minus 2 into this, and from this term del L x, and we can similarly break up this term del L xi into this into del L x xi plus del L eta this and del L x eta. From this term we can expand this. So after simplification we get using the value, putting the values of xi x, eta x, xi x, eta x from the equation 2, from the equation 2. So we get del 2 del xi square u plus twice x del 2 del eta del xi u minus twice del eta u plus twice x del 2 del xi del eta plus 4x square del 2 del eta square u. We assume here this the second order mixed derivative are same, equal. So del 2 u del xi del eta this equal to del 2 u del eta del xi. So we can write 4x into this. So this is the equation 5 from del 2 u del x square. And similarly we can write del 2 del x del y u equal to del L x del u del y, and value of del u del y equal to from 4 this put here, and this del L x of this plus twice y is partially with respect to x, so twice y is constant, twice y del L x this. So now del L x equal to del L xi into del xi del x plus del L eta into del eta del x, and from this term we get this, and plus twice y from this term, this we del L x of this into del xi del x plus del eta of this del eta del x. Value of xi x, eta x, xi x, eta x from 2. Putting all these values after simplification we get minus del 2 del xi square u minus 2 into bracket x plus y del 2 del xi del eta u minus 4xy del 2 del eta square u. Number 6. Similarly we find del 2 del y square u, this. So finally we get this 7 del 2 del xi square u plus 4y del 2 del xi del eta u plus 4y square del 2 del eta square u plus twice del eta u. Using 5, 6, 7 from the given equation, this. So y uxx plus x plus y uxy plus x uyy. So put all these values in the given equation, we get y into uxx, x plus y into uxy plus x into uyy. And after simplification we get this equal to x plus minus x plus y whole square u xi eta minus y minus x bracket into u eta. Now y minus x equal to xi, this is cancel, y minus x square and y minus x, so y minus x equals to xi, this minus minus plus, so we have put here xi equal to y minus x. So this is the required canonical from this equation 8. Hence this can be written as del L xi of xi del L eta u. Integrating we get xi del L eta u equal to phi eta, because this partial derivative with respect to del xi with respect to xi. This phi is an arbitrary constant. Again integrating we get this equal to u equal to 1 by xi, this 1 by xi integration phi eta d eta plus psi xi, because they are partially differentiating with respect to eta. So this is the psi j. Psi is an arbitrary function. So u xy is the j is the y minus x, 1 by y minus x, integration pi, eta is the value y square minus x square, and d of y square minus x square plus psi of y minus x. This is the required solution of this equation 8, canonical form of this, or that is the given partial differential equation. Next question, question 5. A stretched string of finite length L is fixed at its ends and is subjected to an initial displacement ux0 equal to u0 sine of pi x by L. The string is released from this position with 0 initial velocity. Find the resultant motion of the string. Consider this is the actually string, this string problem. Stress string is the one-dimensional wave equation here. So one-dimensional wave equation we can write utt equal to c square uxx, where 0 less than x less than capital L, length of the string is L, and t is the time variable is greater than 0. Equation 1. C is the wave speed. This is the 0 to L. Now the boundary conditions are u0t equal to 0, fixed node at the point x equal to 0 when t greater than equal to 0, t is greater than equal to 0, and ult at the fixed node at the point L, this for all t. So these 2 points are fixed. So at the point 0, at the point L, this string is fixed. So this boundary condition is, and the initial conditions are ux0 equal to u0 sine pi x by L. This initial step, it is given this at the point t equal to 0, ux0 equal to this. This is the initial condition at time t equal to 0. And utx0, that is del tu, this is the equal to 0, as the string is released from the position at time t equal to 0. This is the 0 initial velocity. This del tu equal to the velocity. So 0 initial velocity, so this is equal to 0. This is the initial condition. Initial conditions means for t equal to 0, and when t not equal to 0, the boundary conditions here. Consider the solution of the form uxt equal to capital XX, capital TT, separation of variable method. Then from 1 we get this capital X t double dash. T double dash means d2 dt square capital T equal to c square capital X double dash. Capital X double dash means d2 x square capital X into T. So this is equal to capital X double dash by capital X equal to capital T double dash by c squared capital T. This is equal to minus k square c. Using minus k square, this negative, this gives the correct solution form of the physical perspective. If you take this positive, so we cannot get the correct physical solution. This. So for correct physical perspective, we assume this equal to minus k square. Then x double dash plus k square x equal to 0. Hence solving this second order homogeneous differential equation, x of capital X equal to c1 sine kx plus c2 cos kx, and from this t2 t double dash plus c square k square t equal to 0, capital T equal to c3 sine cket plus c4 cos cket, where c1 c2 c3 c4 are arbitrary constants. Hence 2 becomes, 2 means u equal to capital X into capital T. So capital X is this and capital T equal to this. So we get u equal to c1 plus c2 into this bracket, c3 into this plus c4 into this, equation 3. Now from the boundary condition 1, u0t equal to 0. So u0 t equal to 0. So put here x equal to 0 here. So this is equal to 0. So obviously this not equal to 0. So obviously this C2 constant obviously 0 as is defined for all t. And boundary condition 2, that is ULT equal to 0. So put x equal to L. So this C1 sin KL into bracket this equal to 0. Now this bracket term is not equal to 0. So obviously C1 sin KL equal to 0. But if C1 equal to 0, then this solution is trivial solution. So we are interested for non-trivial solution. So for non-trivial solution, C1 must not equal to 0. Must be not equal to 0. Otherwise trivial solution. So obviously sin KL must be equal to 0. So sin KL equal to 0 means KL equal to n pi, n equal to 1, 2, 3, and k equal to n pi by L. So solution, put k equal to nl by pi. This, so C1 sin n pi Lx into bracket C3 sin C into n pi L. Value of k is this n pi L, n pi by L t plus C4 cos of n pi by L t. Differentiating 4 partially with respect to t. So ut xt equal to C1 into this. So this into this C into n pi by L bracket this C3 cos Cn pi t by L minus differentially cos is minus sin this, and this Cn pi by L taking common from this. Hence using the initial condition 4 is this ut x0 equal to 0. So put here t equal to 0, so we get this equal to 0. So C1 into C3 into n pi CL sin n pi x by L equal to 0. So C3 not equal to 0 because C1 not equal to 0 already we get, and sin n pi x by L not equal to 0 as it is the defined for all x. So C3 must be equal to 0. Hence this becomes this means actually this is the equation 4. Actually equation 4 becomes uxt equal to C1 sin n pi x L into C4 cos n pi ct by L. So we can put here Cn equal to C1 into C4. So Cn sin n pi x by L cos n pi ct by L, equation 6. By principle of superposition, the general solution is given by uxt equal to summation n equal to 1 to infinity Cn sin n pi x by L cos n pi ct by L. Now the initial condition 3 gives this ux0 equal to u0 sin pi x by L. So this t equal to 0, putting c t equal to 0. So t equal to 0. So this cos 0 is 1. So from 7 we get summation Cn sin n pi x by L. Now this equal to u0 sin n pi x by L is given for t equal to 0. ux0 equal to this. This is an identity. Hence, comparing the coefficients of C1 this, so we get from expanding this C1 sin pi x by L plus C2 sin 2 pi x by L plus ... and this equal to this. Just to expanding this. So comparing the coefficients, we get this sin pi x by L, here sin pi x by L right hand side and left hand side this. So C1 must be equal to u0, and this term C2, C3 are all constants are 0. So C1 equal to u0 from this. So equation 7 becomes uxt equal to u0 sin pi x by L cos pi ct by L. From 7 we get all other constants C2, C3, C4 all equals to 0. Hence this is the required displacement This is the answer, required displacement of this. Next question, question 6. Solve the following initial boundary value problem. Ut equal to 4 uxx 0 less than x less than 1, t greater than 0, ux0 equal to x square bracket 1 minus x 0 less than equal to x less than equal to 1, u0t equal to 0, u1t equal to 0 for t greater than equal to 0 by variable separation method. Now this partial differential equation, actually this is the heat conduction equation. Ut into 2 square uxx 0 less than x less than 1 less t greater than 0. Here boundary condition u0t for t not equal to 0, this equal to 0 and this equal to u1t, t greater than equal to 0. And initial conditions here ux0 equal to x square bracket 1 minus x 0 less than equal to x less than equal to 1. Assume the solution uxt is separable, so uxt equal to capital X into capital T. Hence equation 1 becomes this x t dash equal to 2 square x double dash t. This implies x double dash by x equal to t dash by 2 square into t equal to lambda c. So x double dash minus lambda into x equal to 0 and t dash minus 2 square lambda into t equal to 0. Equation 4. Case 1, when lambda is greater than 0, then general solution of 1 is this. Sorry, this general solution of 1, not this 1, actually general solution of this, because this x double dash minus lambda x, so this auxiliary equation m square minus lambda, m equal to plus minus root lambda, so c1 e to the power root lambda x plus c2 from, so not 1, this is actually, this is the 4 from 4. General solution 1 is this using 4 from 4. Okay, this is the correct general solution of 1 by this. So actually we find this general solution of this and general solution of this and then multiplying this, which is the 1. It is okay. General solution of 1 is this, and from this is the first order partial differential equation, so we get m minus 2 square lambda, and so we get c3 to the power 2 square lambda t. c1, c2, c3 are arbitrary constants. This shows that as t tends to infinity, e to the power 2 square lambda t tends to infinity, because lambda is positive, so this quantity tends to infinity, that is unbounded. So unbounded temperature for large t is the t for temperature, which is physically impossible. So lambda greater than 0 is not possible here. Next case, lambda equal to 0. In this case, when lambda equal to 0, so put this lambda equal to 0, so x double dash equal to 0 and t dash equal to 0. So in this case, we get general solution this. So multiplying this, so xx and tt is equal to c4x plus c5, and c4, c5 are arbitrary constants. Clearly this solution is independent of time t, so which is impossible. So only possible case is this lambda less than 0. Case 3, set lambda equal to minus mu square. Mu is a real value. Then equation 4 becomes lambda equal to minus mu square. So from 4 becomes x square plus mu square into x equal to 0, and t dash x square, not x square, x double dash. Sorry, this is the x double dash here, not x square here, x double dash. That means d2 dx square capital X, x double dash mu plus mu square x equal to 0 plus and t dash, that is ddt of capital T plus 2 square mu square t equal to 0. And solving these and these separately, we can get the general solution. 1 uxt is equal to capital A cos mu x plus capital B sin mu x bracket into c into e to the power minus 2 square mu square into t, where A, B, C are arbitrary constants. Now boundary condition u0t equal to 0 So put here x equal to 0. So we get a plus b into c e to the power minus this. Since this is not equal to 0, e to the power minus 2 square u mu square t. So a must be equal to 0. So this equation 9 becomes b sine mu x into c e to the power minus 2 square mu square into t. Now boundary condition u1t equal to 0. So put here x equal to 1. So put here x equal to 1. So sine mu x equal to 1 here. So this since b not equal to 0, because otherwise trivial case, and this e to the power minus 2 square mu square t not equal to 0 for all t greater than equal to 0. So sine mu must be equal to 0. Hence sine mu equal to sine n pi, n equal to 1, 2, 3, 4 dot 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 integers, and mu equal to n pi. Then 10 becomes uxt is equal to cn. Cn, this is the cn, this b into c combined this cn, say cn. Sine n pi x is sine mu for n pi, and e to the power minus 2 square, and this n square pi square value of mu square into t. Equation 4, n equal to 1, 2, 3, 4 dot 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 dot, where cn equal to b into c is an arbitrary constant. By principle of superposition, we get uxt equal to summation n equal to 1 to infinity cn sine n pi e to the power minus 2 square n square pi square t. Now the initial conditions ux0 equal to x square bracket 1 minus x, that is put here t equal to 0, t equal to 0, e to the power 0 equal to 1. So summation cn sine n pi x equal to this. 13 is a convergent half range Fourier series in the open interval 0, 1. Then the coefficient of cn's are given by cn equal to 2 by 1 integration 0 to 1 fx, fx means x square 1 minus x sine n pi x dx. So after simplifying, we get this equal to my 4 by n cube pi cube, n equal to 1, 2, 3, 5, 1, 3, 5, and this equal to minus 12 by n cube pi cube, n equal to 2, 4, 6, and dot 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 dot. Then the details calculation is this. Here value of cn this, and from 12 this we get uxt equal to summation n equal to 1 to infinity minus 4 bracket 1 plus 2 cos n pi, actually minus 1 to the power cos n pi, n cube by pi cube sine n pi x. So this is the sine n pi x, this sine n pi x into this from 12 e to the power minus 2 square n square pi square into t, and this is the required solution of this. Thank you for watching this video.